Hi, welcome back to my channel, and for today's video, we will be talking about the limit of a function. So for those who are new to my channel, don't forget to click down there for you to subscribe. In that way, you will be able to be updated on a lot of videos that I'll be uploading soon. And for those who have been here for a very long time, thank you so much for your support, and thank you for messaging me that I'm gonna provide you a video about the limit of a function. So here's now the video and enjoy watching. Okay, so now let us talk first about the intuitive idea of a limit of a function. So it says here that suppose we have a function f of x defined when x is near a. So what we can do is we can make the values f of x as close to L as we want by taking x sufficiently close to a but not equal to a. And then we write this symbol. So that's actually the limit of a function f of x as x approaches a, and that is our L. So let's consider this graph as an illustration. So let's suppose that we have this f of x here, assuming I have a perfect drawing. So I have that one. And suppose you have a point x here. So the concept or the notion of your limit intuitively is that you, as you find all the values from the right of x closer to x, and from the left of x closer to x, you would actually find a value of f of x corresponding to this point here. So that's the intuitive definition of a limit of a function. Okay, so suppose for example we have the f of x here equals 1 over x plus 1, and then we are interested for example about the limit of f of x as x approaches 1. So what are we going to do with that is we have to take all the values greater than the value of 1 and less than the value of 1 but not equal to 1. So to be very clear on that, let's create a table here with the corresponding value of your x that is less than 1 here, and another table with the corresponding value of your x that is greater than 1. So in this case, we're not taking about the value of x here which is equal to 1. We're only taking those that are less than or greater than the 1. So let's have 0 0.5. And I'm going to approach this to 1. So I would have to make the value of x closer to 1. So I have 0 0.7, I have 0 0.9, I have 0 0.99, I have 0 0.999. So if you see, there's no x here that is equal to 1. So you can do that on your own calculator. I have prepared a calculations for that. When it's 0 0.5, I would get 0 0.667. I would get 0 0.588, and I would get 0 0.526 when x is 0.9. I would get 0 0.5025, and I would get 0 0.5003. Also, when I choose all the values of x greater than 1 here, I'll start with 2 and I'll make it closer to 1. So I have 2, 1.5, I have 1.3, I have 1.1, I have 1.01, I have 1.001. So I would get, when it's 2, it's 0 0.333. When it's 1.5, it's 0 0.4. Then it's 0 0.435. Then 0 0.476. I would get 0 0.49975. And I would get 4.99. I'm sorry. Oh, it should be 19 here, but here it's 975. So that will be the corresponding value for your x when it's greater than 1, but you're making all the values closer to 1. So if you notice, as you approach the value starting from 0 0.5 to closer to 1, so you're approaching to 1, the value here approaches to 0 0.5. Similarly, as you approach the value closer to 1 from the right of 1, the value of your f of x approaches to 0.5. Therefore, it says here that the limit of your f of x as x approaches 1 from the right and from the left of 1 is 0.5. So basically, the value is 1 half. That's it. Okay, so I already also have prepared here and already made calculation here. So our f of x here, supposing that this is x minus 1 all over x squared minus 1, and we're interested when the limit of the function as x approaches 1. So I have prepared a calculation here, taking all the values of x less than 1 and taking all the values of x greater than 1. Now, if you notice, this is just via calculator, so you can do that on your own to verify if my calculation is correct. So when x is 0.5, I get this value, and so with this. And I started with 1.5 and I approach all the values of x closer to 1. So I would end up 1.0001. Although I can think of any other numbers, but the pattern will actually tell you that these numbers here are already enough for you for me to show that the limit of the function is this one. So if you notice, as x approaches to 1, so you start with 0.5 and goes to 0.9999 closer to 1, your value of your f of x approaches to 0.5. Similarly, as your x approaches to 1, so you start from 1.5 and then goes to 1.0001, then the value of your x approaches to 0.5 as well. Right, this value is closer to 0.5. So therefore, it simply tells us that the limit of the function is 0.5. That's it. Okay, so to make clear on things about this, before we proceed with the formal definition of a limit of a function, the implication of the limit of a function is that, say for example, we are asked to solve for the value of the limit of f of x as x approaches 3. So intuitively given, the function f of x as x approaches closer to the value of 3 from both sides, the question that we are actually answering is that what is the value of f of x approaching? That's it. Okay, suppose we have, for example, the graph of a function f here. So entirely, this is our graph of a function f. Assuming I have a perfect drawing. Sorry for that. But anyway, yeah, suppose that is our function there. If we are interested to find the limit of our f of x as x approaches, let's say 1, negative 1 from the right. So this is actually our negative 1. So as x approaches negative 1 from the right of 1, negative 1, so we would get the value equal to 1. Okay? Now, how about if the limit of x as x approaches 1? So that's the limit of f of x as x approaches 1 rather. Now, if you unlike with this one, there is a corresponding plus sign on top of 1. So that is, there is an exponent plus on your negative 1. In this case, I'm sorry, this is negative 1. So in this case, there's no indication whether it's plus or minus. So that means, what does it says there? It simply tells us only that we're actually taking both sides of negative 1, like what we have done earlier when we are interested to find the limit of f of x as x approaches 1. We're actually taking both sides, the right and the left. So in this case, starting from the right of negative 1, that's actually 1, like what we have solved here. However, starting from the left of 1 going to negative 1, the corresponding value is 3. So if you notice, they're actually not equal. Now, from our previous example wherein we create a table, the corresponding value when it's less than 1 or greater than 1, they're actually equal. In this case, however, it's not equal. So therefore, the limit does not exist. They're actually not existing on this specific function. So the limit does not exist. So I would denote that by D and E, does not exist. Okay, how about if we are interested about the limit of f of x as x approaches, let's say 4. Now, if you notice, this is 4 here. However, when the graph approaches to 4, this is asymptotic to 4. It never touches to 4, assuming I have a perfect drawing here. And it never touches to 4, but it's asymptotic to 4. So that means it goes to down to forever. Although, intuitively in our life, there's no such thing as forever. But anyway, if you notice here, it goes to forever without bound. So technically, that means it's negative infinity. Okay, so what does it simply tells us? This is unbounded behavior. It's not actually saying that the limit exists, but it's telling you in a manner that it does not exist. But there's actually a negative infinity that we can represent for the limit of the function f of x as x approaches 4. That's it. Okay, so let's go now to the definition, the formal definition of the limit of a function. So we call this formally as epsilon-delta definition. So I'm really sorry for my penmanship there. I really can't control my pen. But anyway, that's the formal definition of a limit of a function. Okay, so let f of x be a function defined on an interval that contains x equals a, except possibly at x equals a. So we don't care about the value x at a. So then we say that the limit of f of x as x approaches a is L if for every epsilon greater than 0, there exists a delta greater than 0, such that this absolute value of f of x minus the limit, so that's minus L, is less than epsilon whenever you have this inequality here. Okay. So let's consider, for example, we have this graph. Suppose this is the graph of a function f of x. Okay, this is our a here. Okay. Okay, what does it say? It says here that if our epsilon is greater than 0, then we can go to our graph and sketch two horizontal lines. So we have the horizontal lines L plus epsilon and corresponding to L plus epsilon and L minus epsilon. So let's say I would have here L plus epsilon. I would have here L minus epsilon, assuming I have a really good drawing here. So we can create a horizontal line corresponding to that. So assuming I have a very straight line here perfectly. So that one. Okay. Okay, that's it. Since we have created the horizontal line corresponding to L plus epsilon and L minus epsilon, so it says there that somewhere out there along your A, you can find a delta greater than 0. That in that way, you can create also a corresponding vertical line for, let's say, A plus delta and A minus delta. Assuming the distance here is equal. I'm sorry, I made it not so perfect drawing, but technically assuming these are equal. So I would have this horizontal vertical line here corresponding for A minus delta, and I also have A plus delta. Okay. So if we pick so what does it mean? So if we pick X here between the region, then X will be closer to A. So since X will be closer to A, what we can have is that we would be sure that this is okay. So that means this thing here exists. Okay, so if we now identify the point on the graph that our choice of X gives, that then this point lie on the intersection of this region. So you would have a certain point here that lies on the intersection of this region, which simply tells us that this exists. So that means the absolute value of your f of x minus your L is less than epsilon, because the point you when you choose your x there, it lies on the intersection here. So you are pretty sure that this actually is valid. That's it. Okay, so observe that there could be an infinite number of possible deltas we can choose, and observe also that the definition is actually telling us that we really need to make sure that the function is defined on some interval that around x equals a, although we don't really care if it is defined on x equals a, but we have to make sure that the function is really defined on the interval around x equals a. That's it. Okay, so let's consider this. For example, it says here that the limit of 5x minus 4 as x approaches 2 is 6. Then we have to show that that is actually true. I know you what you're thinking. You just have to substitute 2 to the 5x minus 4 and then you get 6. Um, that could be a coincidence, but not at all times you have to substitute, then you get a specific value. So of course we have to follow the definition, the epsilon delta definition of the limit of a function. So what's the point? We're actually getting those definition if we're not using that. So we have to use the definition for us to show that the limit of this function is equal to 6. Okay, so to start with that, we assume that our epsilon is always greater than 0. Then we have to choose a delta. Remember that our delta is always greater than 0. So in this case, we don't know what could be our delta. So what we're gonna do with that is we choose delta equals something. So let's leave it there and we'll go back to that later. So we have this something. Okay, now, so our goal is to end up less than epsilon. So note that, remember on the definition, that's gonna be the absolute value of f of x minus L is less than epsilon. So that means our f of x is 5x minus 4 minus 6. So that is our L here. So this is equal to 5x minus 10. And this is equal to 2 times x minus 5. So how can we end up having this as less than epsilon? Okay, remember that on the definition we have f of x minus L, and this should be less than epsilon. Sorry, whenever x minus a is less than delta, it's greater than 0. So our a here is 2, right? Oh, I'm sorry. Let me correct this one. This should be 5, and this is x minus 2. Thanks for that. Okay, so this is 5x minus 2. So therefore, this is already less than delta. Okay, so how can we end up that this is less than delta? So that's 5 with delta less than epsilon. So we need to assume that our delta is equal to epsilon over 5. Okay, so that our this becomes 0 x minus 2 less than delta is epsilon over 5. So therefore, this x minus 2 is less than 5 times epsilon over 5, and this is equal to epsilon. So therefore, this thing here is less than epsilon, and so this claim is true. That's it. Okay, so let's consider another example here. So we are interested to show if this is true, that the limit of x squared as x approaches 0 is 0. So to show on that, again, let's start with assuming that epsilon is greater than 0. Then we have to choose our delta equals something. So we're not sure for that yet. So what's that? What does it say there? Okay, we have this equality, and so this will be our end. X squared minus 0, because remember this is our f of x, this is our L, and so we can write this as x squared. And remember that the absolute value of x squared is actually the square of the absolute value of x. Okay. Now, how can we end up that this thing here is less than epsilon? Okay. Remember that we could have epsilon greater than x squared, which implies that square root of epsilon is greater than the absolute value of x. Why? Note that if we have this x squared less than epsilon, because this is our goal here, to be less than epsilon, this would simply tell us that x is less than square root of epsilon. And so remember that we have this 0 less than x minus 0 plus this one. And this implies that this is less than delta. Okay? So therefore, we take our delta to be square root of epsilon. Okay? So if you have any question, please comment down there so that we would know in order for us to clarify on that thing. So now that we have this one here, so we're pretty sure that this is less than the square of the square root of epsilon. And the square of the square root of epsilon is equal to epsilon. So therefore, this is less than epsilon. And so this is actually true. That's it. Okay, so we will consider one last final example. Okay, so we will have to prove that the limit of 4x plus 1 as x approaches negative 1 is negative 3. Okay, so again, let's start with assuming that epsilon is greater than 0 and we choose our delta. Okay, in this case, we don't know yet what our delta is. So we assume here, remember that this is x minus negative 1 because this is our a here. So this is less than delta. This simply tells us that this is equivalent to x plus 1 less than delta. So here, this is 4x plus 1 minus negative 3. And this is equal to, what is this? 4x plus 4, right? And so I can extract 4 here, and so I have x plus 1. And remember, x plus 1 is less than delta. But there's a 4 here, so I can choose this as epsilon over 4. In that way, since this is less than delta, I would have less than 4 times epsilon over 4, and this is equal to epsilon. So therefore, this claim is true. That's it. Okay, so that's all for now. Thank you so much for watching. So for today, we have learned about the limit of a function both intuitively and its formal definition. So thank you so much, and I hope you enjoyed the video. So if you have any questions, clarifications, you can comment down there. And for those who are new to my channel, please don't forget to click down there to subscribe so that you will get updated on a lot of videos that I'll be uploading soon. So thank you so much. Have a great day. Bye for now.